In this video, we're going to discuss the mean value theorem. The mean value theorem is a very important theorem in calculus. Next week, when we do curve sketching, actually later this week also, we're going to do something that technically uses this, even though it may not seem like it. But next week, we will use several results of the mean value theorem in order to figure out how we can sketch a curve. So let's discuss the mean value theorem. Well, before discussing the mean value theorem, let's look at a special case of it. So we first consider Rolle's theorem. Rolle, a mathematician, Rolle's theorem. A special case of the mean value theorem. Mean value theorem could be abbreviated MVT if you don't want to write those words. Rolle's theorem. What does Rolle's theorem say? Well, first of all, we're covering this theorem that I said was a very important theorem in calculus. It's a very important theorem on derivatives. And we're covering it before having ever done a derivative computation. Meaning, the only thing we know about the derivative is that it's defined to give the slopes of tangent lines. And that's actually the only thing we're going to need to know. But what does Rolle's theorem say? Well, I'll give you a couple assumptions. If f of x is continuous, this isn't going to fit on this board. Okay, I'll do it like this. On the closed interval a to b, and f of x is differentiable on the open interval a to b, and if this one shouldn't be a comma, or maybe it should. If f is continuous on closed and f is differentiable on that, I guess this first and just shouldn't be here. And I don't like Oxford commas. There we go. See, sometimes when you're trying to form a sentence, you have to slow yourself down. If f is continuous, and or if f is continuous on f is differentiable on that, and f of a equals f of b, comma, then there's going to be a sentence which takes up another line and a half. But before getting to the then, let's draw what we have. So, back in the last video, I briefly mentioned, I briefly drew a parabola and showed the tangent lines on the parabola. Well, that type of curve will be useful for understanding Rolle's theorem. I'm going to draw it upside down. So the way this should be organized is Rolle's theorem, the statement of the theorem, the rest of this sentence, and then observe right after it. This observation is going to illustrate what this theorem says. But let's draw what we have. We need an interval a to b. Let's throw it in the positive side. You know, that's more convenient. Continuous differentiable, f of a equals f of b. Well, that means our function, f of a equals f of b, means our function hits the same y value. Let's draw a dotted line. Continuous and differentiable. So in the last video we saw that differentiable meant not differentiable, meant it had a corner or a cusp or a vertical tangent. Continuous means you can draw it without lifting or writing it. So we're going to draw a curve through those 2 points, which is continuous and doesn't have a corner, a cusp or vertical tangent. So let's just make it a simple looking one. You know, kind of like let's move that over. So we have this curve. I don't like how that looks. Too flat. I like how that looks. A is here, f of A, f of B, B. And then I'll draw that dotted line again. Because they're at the same y value, and that's going to be relevant for this. And this is f of x. So this is a setup for Rolle's theorem. Continuous function, no corners, no cusps, no vertical tangents. F of A equals f of B. Then what happens? Well, what does the derivative look like in here? What do the slopes of the tangent lines look like between A and B? Well, let's take a look at them. Start at A. It looks like this. Let it travel through the curve until it gets to B. So this, maybe my arm was in the way. Tangent line at A. Let it travel through the curve. I was staying on the curve much better with my arm. Maybe I'll try it like this. Start at A, let the tangent line travel through the curve. And let it travel back. What happens in the middle? Well, what happens somewhere in the middle, I should say. Well, I drew that dotted line for a reason. What happens in the middle? What definitely happens in the middle, I should say? Well, there are a couple things you could say definitely happen. But notice what happens here. Notice what happens there. We have a tangent line which is parallel to the dotted line. And that is always going to happen with this setup. You're always going to get this tangent line which is parallel to that line. Let's write that with calculus. Then, that tangent line exists. So then there exists what does there exist? How can we say that tangent line exists with a derivative? Well, let's draw the tangent line. That line is parallel. What is the derivative of that line? Well, what is the slope of that line, I should say? Well, the slope of that line is the derivative at this value. This is a value which exists. There exists an x value where this occurs. Let's call this x value c, because that's standard. There is an x value at which our tangent line is parallel to that dotted line. So there exists a c in A to B such that what? Such that the slope of this line equals the slope of that line. Well, we can write the slopes of both of those lines. The first one, the top one up here, what's the slope of that line? Well, you may look at that and say it's horizontal, so it's 0. What is the slope of that line using calculus? What are we showing here? We're showing that this exists. The slope of this line using calculus is the derivative at c. The slope of that line is the derivative at c. We have two parallel lines. Their slopes are the same. I'll mention something about that symbol in a moment. The slopes of these two lines are the same. What's the slope of the dotted line? Well, 2 points on the line, their y values are the same. It's a horizontal line, so you could use the change in y over the change in x, so you get 0 over some non-zero, or you could just say it's a horizontal line, so the slope is 0. Now right here we have a statement of Rolle's theorem. Given these three assumptions, we can find a point in the middle where the derivative is 0. And we can set up that equation using calculus and, I guess, algebra, line algebra. Now this symbol here, I guess I'll just write it up here. You can write this Maybe you should like draw an arrow pointing to that symbol. That's not a C. That symbol in math means in. So I'll say this is read in. So in that sense, then there exists a C value in the interval a to b. So C is in this open set, or open interval, I guess I should say. There exists a C in here where that's true. Now, let's take a look at these assumptions. Now that type of graph illustrates Rolle's theorem. What happens if the function is not differentiable? Why would this not necessarily hold? Well, let's take a look at one. So let's just say, observe Rolle's theorem, the conclusion of Rolle's theorem doesn't hold if f is not, doesn't necessarily hold if f is not differentiable. Differentiable is a really long word. DIFF works fine. Observe DIFF colon. Well, let's draw it a little bigger. Well, let's take the other two assumptions. If it's not continuous, you could break the function apart so that it still hits those 2 points. Instead of going up here, you can just, have a line through there and a line through here. The lines may not intersect. You could have, actually that's one, you could have 2 parallel lines. Make that a function. Rolle's theorem won't hold. But let's look at differentiability. Differentiable, that's in a way a more interesting one. Let's draw it like this. Right here is a curve which is not differentiable. Here's A, there's our y value, here's B, there's our y value. We have a corner up here now. A corner, remember the derivative doesn't exist there. So there's f of x, not f prime. Rolle's theorem doesn't hold. Why does it not hold? Why is there no value inside a to b where the derivative is 0? Well, there's no horizontal tangent. The derivative at the corner doesn't exist. Derivative over here, we have all these positive numbers. Derivative over here, derivative over here, all these negative numbers. Derivative over here, all these positive numbers. So there's no, let's write it like this. Let's just say there's no value in a to b with f prime. I'll just say where the derivative is. I don't want to introduce another letter for this. I'll just say where the derivative is 0. Alternatively said, there's no horizontal tangent line. The derivative doesn't exist at that top, and for the rest of it, there's no horizontal tangent line. So we do need the assumption differentiable, so that this tangent line could be smoothly approached on both sides. I use the word smooth. Smooth is actually an important word in math. Not in calculus 1, 2, or 3, but in any kind of higher analysis. But for our purposes, we can think of it exactly in a context like this where the tangent lines are traveling smoothly. They don't have to navigate around corners. But Rolle's theorem, as I said earlier, is a special case of the mean value theorem. I'm going to redraw that curve. So let's state the mean value theorem. The mean value theorem allows us to reach very nice conclusions about the derivative. We'll see some of them when we do curve sketching, as I mentioned earlier. Mean value theorem. Well, Rolle's theorem had 3 assumptions. We're going to remove one of them. If f is continuous on A to B and differentiable. I'm going to write the whole word differentiable because this is a large theorem. And great. Differentiable on open A to B. Then, so we're going to keep the assumption that it's continuous, we're going to keep the assumption that it's differentiable, but we're going to remove the assumption that those points are on the same horizontal line. What does that change? Well, these points no longer have to be on a horizontal line. Well, if you wrote this in a notebook, take your notebook. Do I have a notebook? No, but I have notes. Take your notebook and do that. And that's what we have. If you're standing at a board, do, which way did I rotate it? I rotated it that way. Do this. If you do that, if you make this dotted line diagonal instead, then you've removed the assumption that they lie on the same horizontal line. What conclusion can we reach? Well, I'm going to fill in the rest of that board, but let's draw what that looks like. Now with a, maybe I should have said when you rotated your notebook, I guess the x and the y, the x-axis and the y-axis need to stay the same. So really what I should have said is cut out the graph from your notebook and rotate that piece while leaving the x and y-axes the same. Well, let's draw that. So we have those 2 points A and B. Let's still call them A and B. But let's say they're at different y values. This is going to be another where I draw this and then I erase it and draw it like I did the other one. So we have them at different y values. Let's draw a curve with no corners or cusps. And let's connect those 2 points. Well, you could use a line. That's not interesting. It still holds for a line. Let's make it curvy. Let's make it look, I don't know, like that. Actually, that's not that bad. Let's leave it like that. Observe, let's call this f of x. Let's draw it small so it doesn't get in the way. So we tilted this curve on its side. Let's also tilt the dotted line on its side. Great line. I guess that's fine. We'll be able to reach the same conclusion. All we did was tilt this on its side. That same result is going to hold. But what does that tangent line now look like? Well, it's still going to be, well, maybe I won't give the punchline away right now. Let's look at tangent lines traveling from A to B. From x value A to x value B. Start here, travel along the curve until you get to B. Start here, travel, and you'll notice somewhere in the middle you're going to have a tangent line which is parallel to that line. So that conclusion will still hold. Then there exists some C in there where those lines are parallel. So let's write that down. Then there exists a C in A to B such that what? Well, 2 parallel lines, their slopes are the same. What's the slope of this line? The non-dotted line. Well, it's tangent to that curve at C, so the slope is f prime of C. what is the slope of the other line, the dotted line? Well, in this case, for Rolle's theorem, they're on a horizontal line, so we just said the slope is 0. But here, we have 2 points on the curve. We can find the slope using 2 points. The change in y, the curve is defined as f. The change in y, f of that value, or f of that value minus f of that value, divided by the change in x. So we took Rolle's theorem, we got rid of the assumption that that line was horizontal. And we have a very important theorem in calculus, the mean value theorem. You know, it may not seem like it's saying enough, or much, but this conclusion says we can reach nice, this statement says we can reach nice conclusions about the derivative on entire intervals. It tells us a lot of information about what the derivative does on intervals. And when you can tell what derivatives do on intervals, you can kind of piece together intervals so that you get the entire real line. It's a very important result. I personally really like the tangent line observation, or the parallel tangent line observation. I think it makes this equation much easier to come up with. But we'll just discuss one more thing about this. This conclusion says there exists a C. Well, it doesn't say there exists a C. It just says there exists C. Maybe it should say AC. There exists a C. So, from the statement, one C definitely exists. But, in general, you may have more than one. So, another observe. Well, maybe a remark. There could be more than one such C value. As opposed to, well, the theorem guarantees there is at least one. But there could be more than one. And what would that look like? Well, let's look at it for mean value theorem. The same thing holds for Rolle's theorem if you flatten it out. Can I fit this on one board? Yeah, I think I will be able to. Observe this graph. Let's put it over here so it's not too close to the other one. So we have here A and B spread out like that. And let's draw the dotted line again. Because we're going to observe there was more than one such C value using our tangent lines. Well, we need a tangent line parallel so that we can reach the conclusion. How many C values are there? Well, look, there's one right there. Keep going, keep going, keep going, keep going. There's another. So in this case, there are two, and you can see, of course, if we just put lots of waves in there, you could have also more than two, of course. So I'll just mark this off like this. And I'll say 2 such C values. That shouldn't be a period. So the derivative has many useful visuals. The mean value theorem illustrates, I think, the nicest visual of the derivative that we'll see in Calc 1. So do look at curves like this and look at how the tangent line isn't parallel, and then up here it is parallel. Now I think that's a very important visual for any Calculus 1 student. Any calculus student, actually.